Okay, so I need to start with this classical unification scheme scenario about the AGNs. So you see the AGNs are surrounded by, we believe, by a certain kind of obscuration, and we divide roughly AGN in type 1 and type 2 AGN depending if we see the broad line regions or whether we see only the narrow line region. And these objects are linked also to X-ray properties. Type 1 AGNs are not absorbed in the X-ray on average, and type 2 are absorbed in the X-rays. These objects are typically blue. They show an UV axis up to ratio 2.2. Okay, this was the picture about what we knew about complete samples of AGNs back to 30 years ago. These are the 100 quasars that we know these are the PG quasars. Okay, and this is the estimate of the luminosity function 30 years ago by Schmidt and Green. Okay, this is what we have 20 years later. We go from 200 to 24,000 AGNs sampled. And from this large sample of AGNs, we can work out properly the luminosity function in the optical. And we were asking if there was a luminosity evolution or a density evolution in the AGN luminosity function. Okay, this is what we knew in 93. The result by Bolshanks and Peters in 88, our result, and the result by Krum et al. With the 2DS survey in 2004. Okay. As you see, there is a strong evolution going in the past, and we know about that. You can parameterize that in several ways, but the most important thing is that there is a strong evolution going in the past. And as I said already, it stops to this ratio because of selection efforts. It's very difficult to select objects at ratio larger than that because the colors of the AGNs enter the stellar locus. As it was quite difficult to select the high ratio objects. But what about lower luminosity? Are these all the only AGNs we know? So there is this work by Howe selecting AGNs with emission line properties that says that the AGN activity goes also at even fainter luminosities, lower luminosities. Anyway, we were stopped at ratio 2.3 about. What about the high redshift evolution? This is one of the first important results by Smith, Schneider, and Gunn in 1995, in which, using Grism surveys, not longer colors, they probed the density of AGNs at high redshift, and they saw a decline in the density. But there were many concerns if that was a result affected by many selection biases. Similar results was obtained 10 years later by the people working on the slope digital sky survey. This is the slope of this slope is this one by Schneider. So the result was practically confirmed. Similar result was also obtained in the radio. And it was known since more than 30 years ago. This is the evolution of the radio loud AGNs observed by Dunlop and Pickering in the 90s. And at that age, there were hints of a bimodality in the luminosity distribution of the AGNs in the radio. This is the radio luminosities, and this is the optical luminosity. And you see there are indications of that bimodality. That's why we usually say we divide AGNs in radio loud and radio quiet. It is because of this observation in these days. And I'll talk about that in the end of this talk, how much this is an effect of a selection bias because of the scarcity of the statistical uncertainties of the data. Okay, so there was this difficulty in finding higher redshift AGNs, and so a way of selecting AGNs is to use the X-rays, because in the X-rays the ACDs of AGNs are completely different from normal galaxies which are not active. And so people tried to look for the AGNs in the soft X-rays with the telescope that were available at that period. So Einstein, and before that also the HO1 in the hard X-rays. And so this is one of the most important results of that time. And this is the evolution of the density This decrease is the decrease I've shown you before. This is the optical radio decrease observed before, and this is what they get. So they practically they are not able to probe at redshift the luminosity function because they are not hard enough to see the entire population. Moreover, from the hard X-ray telescope, although the PSF was very large, it was not possible to identify the object, we already knew that there was a very hard X-ray background, but which was quite flat, too flat to be reproduced only with type 1 AGNs. So the idea was there is a very hot plasma doing a Bremsstrahlung emission that reproduces the X-ray background, or, and was the first paper of that, there is a second population, a large population of type 2 AGNs which are absorbed with a hard X-ray spectrum that is able, combined with type 1 AGNs, to reproduce the whole X-ray background. Indeed, this is the NH distribution of local sample. We see that we already knew that there was a large samples of type 2 AGNs which were heavily observed. And you see how much harder it becomes the spectrum when you increase the column density. So a lot of papers were produced to reproduce the X-ray background. This is one of the most important ones, but there are many others. And you see how much important it is to have type 2 AGNs in order to reproduce the entire X-ray background. Eventually, we had the possibility to identify each single sources with the new telescope, Chandra and XMM, and eventually we were able to find the type 2 AGNs. This is the new millennium. Actually, we observed we were at the telescope the 1st January of 2000, but the telescope were not operating because we were scared of the millennium bug, so we observed the days before. And you see, it started to appear the type 2 population, and also some objects which don't even show any emission line, the X-ray bright optical normal galaxies. So it becomes much more evident that with only emission lines it's not possible to select all the AGNs. So using the hard X-ray service, we start to have a better picture of the evolution of the AGNs. This is the paper by Weller. And the first time that we see what was called the downsizing in the AGN evolution. These are the low luminosity AGNs, medium luminosity, the higher luminosity AGN, and we have that the peak of the density of large luminosity AGN is at higher ratio than the lower luminosity one. Moreover, it was observed clearly that there is a trend. This is the fraction of the absorbed AGNs as a function of luminosity. This luminosity is corrected for absorption, so it's the intrinsic luminosity. And we see that the fraction of absorbed AGNs is larger at low luminosities, and no trend was observed with redshift. In order to reproduce this evolution, the parameterization is what is called luminosity-dependent density evolution. So you have density evolution which is dependent on luminosity. That's quite simple. With 2 times larger sample, we did the same analysis, and we find again the luminosity-dependent density evolution, the downsizing. But we also found the dependence on the fraction of absorbed AGN with luminosity. But as you can see, this is a redshift, and this is a fraction of absorbed AGN. We also found for the first time that there is an increase of the fraction of the absorbed AGNs with redshift. This increase has been debated since this publication in the last 10 years, but I will tell you about the last result in the next slide. What about the high redshift luminosity function? These are the most important results of the last years. This is from Brusa, Shivano, and Roy, and all they agree with the decline of the density of AGNs. Quite similar to what I've already shown you before, observed only for the type 1 population. This is what I showed you for the optical, type 1 AGNs, and for the radio. So we are pretty sure that, and this is a very clear result, that we are now probing also the decline of the density of the AGNs at a high redshift. So what about the evolution of the absorption fraction? So this is a work done by my PhD student. This is the dependence of the fraction of the absolute agents with luminosity, and this is a low redshift, and you see the same trend is the same also going to, this is a higher redshift beams. And this has been also confirmed recently by the work by Weger et al. A few months ago. So the increase of the fraction of the absolute agents with redshift is robust, I should say now. I think that part of these results comes also from the contribution of the hosting galaxies, because we know that high redshift galaxies are much more dusty, so it should be both a contribution of the change of the covering factor and the absorption by the hosting galaxy. And this is the best result we have now about the evolution of the Ricci function in the X-rays is a few months ago by Ueda. You see again the downsizing, but I want to draw also your attention to this very marginal, maybe not statistical significant increase of object, because they say, and I report what they say that we are starting to see an upsizing evolution at very high redshift, in which the more the ratio of less luminous AGNs to more luminous AGNs is larger at early epochs. So we are starting to see the hierarchical part of the evolution of the AGNs, because you see the downsizing is anti-hierarchical.
Are these results corrected for the obscuration that you just mentioned? So when people plot these downsizing plots, do they correct for the obscuration?
Absolutely. This is luminosity corrected for absorption completely. So everything is corrected for absorption. All you see here are luminosity corrected for absorption. There is not the absorption here. I mean, you can discuss which K correction do you use to correct for absorption. So which spectrum, I don't know if I had it. Which spectrum do you use to correct for absorption? You can change the recipe, this recipe.
Sorry, I mean about the number of objects that are actually obscured and they are not observed. Because in the original,
Go ahead.
I think in the original X-ray luminosity functions that showed the downsizing, there was no correction for an obscured fraction of objects.
No, absolutely. No, there was. The way the one takes into account of the obscuration. I take into account obscuration. Ebrero takes into account of obscuration. Also
You just showed the common density distribution in the local universe, right? Can you go back to that plot? I mean, it doesn't turn over. So there could be some arbitrarily large
which counts?
Show the common density distribution that you showed in the local universe. You showed that there's no cutoff, so there could be an arbitrarily large Compton thick population here.
Oh, yes.
Right?
This is another part. We are talking about Compton thick objects. If you talk about objects larger than 24, you can put a huge density of objects with this density. You can do, maybe I'll discuss about that later. It's true. But, well, it's everything what I told you is more or less true till density of 24, 25 in common density, 10 to the 24, 25. But 24, let's say, okay, to be sure. So objects which have this spectrum. When you go to the very Compton thick objects, you don't know how much large is the reflection component. You can have very obscured objects, so much obscured that you don't see in any wavelength at all. There is space for that. But we can check if how many of them can exist later. I'll discuss about that. So everything here is corrected, as I told you, for obscuration, and Weida takes this into account. And I was discussing about this possible first observation of the upsizing at the very early epochs of the AGN evolution. And this is what we are talking about. So you can reproduce the X-ray background, but there is a degeneration in the spectrum of the heavily Compton thick objects, because they are so absorbed that the only part that we see is the reflection part. And you can play how much intense is the reflection part. Okay? So you can increase or decrease this number by a large fraction. But, you can say that there are 10 times more objects than what we have already observed. Let's see about that. Okay, we have been looking for very heavily obscured sources, and as they are not easily, it's not possible to see them in the X-rays. We try to looking for evidence of obscured AGNs, looking at the infrared colors, using Herschel and Spitzer data. And there is this kind of work, that you have the references, is in which you select the object which show very hot dust compared to object with warm dust, and you stacked in the position where the objects are, but you don't see the X-rays data, the detection, so you just see nothing, but you stack several objects, and you start to see that those objects are typically have also a hard X-ray component much more intense than a control sample. So those objects, which are much more red, with much more hot dust, are hard X-ray ratio that's typical of very obscure source. But if you make the computation of the density, you don't go outside what you expect for the evolution of genes, which we have already measured. So we don't find evidences of a very large population of sources that can change our picture on the evolution of the genes up to now. So you can observe the evolution of the genes in several ways, in bolometric, X-rays, of X-rays, B-band, and you see the downsizing in every band. This has been done also for type 2 genes by Bongiorno, and you see the downsizing of the type 1 genes only. But in order to work out the bolometric luminosity function, which is quite important to discuss the energy budget of the genes, you need to know the bolometric correction. And you see there are several works on this, and there are several sentences on which recipe to use to work out the bolometric luminosity function. This is one of the last results in which you still see the downsizing is at the lower redshift beams. The downsizing is still confirmed. 4 minutes. Perfect, thank you. And as already you showed us, we see in using a sample about 40-50 objects, which we are able to probe the mass of the black holes using because we are able to probe the sphere of influence of the GNs. We see this scale relation between the black hole mass and the stellar dispersion of the bulge, the luminosity of the bulge, the mass of the bulge. Okay. Using these relations, it's possible to observe the local galaxy luminosity function and to derive the local black hole mass function. And this is what we get. This is the local black hole mass function, not looking at the AGNs, but looking at all the galaxies, uses the scalar relation I showed you before. Okay? And this is the X-ray background. Any evolution model of the AGNs should reproduce these two quantities. This is the integral of all the accretion, and this is the integral of the accretion on the time, because this is the integral of all the luminous activity of the AGNs. Okay. So this is kind of job has been done several times. This is called the Sultan argument. So you have to solve this equation, which the efficiency enters, and you have to solve the continuity equation. And you can do this with the luminosity function. You can use the luminosity, you can compute the luminosity density, you convert it in the accretion rate with the bolometric correction factor and efficiency, and you get mass density. This is the evolution we get, for example, with our best fit luminosity function. You get at the end, this should be the density the local density of black hole in the universe, and these are recent estimates that more or less are in agreement with that. So again, if we have a very huge quantity of comptotic AGNs, this number should be lower than this. Okay. If we had 10 times much more comptotic AGNs, this number would be 10 times larger. Okay. So there is no room for so many comptotic AGNs, which have accreted a lot. Okay. And you can play much more better trying to reproduce the Wool mass function. This has been done by Marconi, and you have to work on the luminosity Eddington ratio and the efficiency. These are the best fits using different evolution models of the AGNs. The problem is that when you do this kind of job, you need to know the distribution of the Eddington ratio. And it's very difficult to measure the distribution of the Eddington ratio. Many measures are based not on the measure of the black hole mass itself, because it's quite difficult to do. You need to know at least to see the broadline regions. You don't see that, for example, in type 2 AGNs. At the moment, the only way to measure the black hole mass, or either you see the broadband region and you restrict it to the type 1 GNs, or either you use the relationship between the bulge and the black holes, but you don't know if this is valid for type 2 GNs and if it is valid at array shifts. And you, for example, you see how much different are the results using galaxy mass of stellar dispersion. These are two different results. So there are very large uncertainties, not on the luminosity function of the GNs, but on the deriving the mass function of GNs. This is the problem now, I think. Okay, I'm finished. Is this relation, this is the local relation, is this evolving with time? This is a study that has been done for several years, in the last 10 years, and there are indications that the fraction of black hole mass compared to the bulge mass is larger in the past. But you see how much larger the statistical certainties are, so it's quite marginal as a result. So I finish here. I'm showing this fit on the evolution of the black hole mass GN. We see as the downsizing, this is redshift, and this is the final mass of the GNs, in which the larger mass reach their mass at higher redshift than the lower mass. This is the black hole mass function, which increases with time, and this is the duty cycle, which is lower at low redshift and increases at high redshift. I skip and the part of the radioluminosity function, which we are able to reproduce, and the kinetic luminosity function, in which we were able to reproduce the kinetic luminosity function using the radio distribution. And so, just to say that, this is why we say that, that the bimodal distribution is no longer true, is no longer, doesn't mean anything to say radio loud. Distribution of the radio distribution is continuous. You have just to decide a threshold. Okay. And I go to the conclusions. And this is that, these are the conclusions. I stop here. Okay.
I wonder if you can comment on the tension between the results from X-ray surveys, which show a steep decline of the type 2 fraction with luminosity, and the radio and infrared and optical surveys, which show this basically flat 0.5, 50-50 ratio between type 2s and type 1s, going all the way to the highest luminosity.
Okay, for the optical, I don't think so, because it was already observed from paper by Lawrence that the luminosity dependent, the fraction type 2, type 1 depends on luminosity.
Well, I'm looking at Lawrence and Elba's paper, in which they show a plot in which, all the way up to 10 to 47 hertz per second, it is flat with the results from a suite of infrared and optical and radio surveys. And we, in the optical, demonstrated from Sloan data that at 10 to 46, 10 to 47 hertz per second, the fraction is about 50%. And when we look with Chandra at the highest luminosity optically selected obscure quasars, we find that at least 50% of them are quantum thick. And so I'm wondering if this is entirely due to the quantum thick population, or is there something else going on?
I don't think it's because of the quantum. No,
That argument is based on the X-ray background.
Sorry?
Your argument that there's not a large quantum thick population is based on the X-ray background and on the local black hole mass density, correct?
Mainly on the local black hole mass density, because you can still add a lot of quantum thick GNs without changing too much the X-ray background.
But do we really know the local black hole mass density?
No. This is the picture up to now. No, absolutely. I told you there is room if you want to add many of them, but if you use the bulge black hole scale relation of today and believe it, you know the black hole mass density today.
I just want to add a small comment to your actually, because in Cosmos we actually found that the obscuring fraction is varying with X-ray luminosity, but it's much flatter.
Okay.
And the luminosity of 10 to the 44 up to 10 to the 45 x per second to the NKD, the fraction of obscuration is about 50%. So this is This is from Cosmos, using an ST approach. If you use a demographic approach, the situation is different, because you are counting. So,
But when we use X-rays, we should correct for selection effect due to absorption. Okay?
and this is what we see.
Okay.
Yeah.
Okay. Let's see. Equal.
Short question. The
Yeah.
two Hopkins has a model for evolving weight luminosity function.
Sorry?
2007-2008. Two Hopkins.
Yeah.
You published a model for the evolving weight luminosity function, which theorists like to use because it's very convenient. So how does it compare?
The one by Hopkins,
Yes.
I think it's compatible because more or less doesn't.
I think whatever, parameterization, whatever called, something which is easy to use.
I think my impression is that the major area where the new observations have improved and don't quite agree with the fits in that paper is actually the right end at high Z, where there was a very shallow slope fit in that paper, the right end luminosity function at high Z, basically because we were just extrapolating fits from low Z. So if you use it above Z of 2, I'd recommend updating the newer data.
Okay, then let's thank Fabio again.